Hello, guys. Thanks for joining our talk today. We are Ikigai Labs. My name is Jaehyun Sim, and I'm a software engineering manager here at Ikigai Labs. And I'm joined by our infrastructure engineer, Amar Shah. And today we're going to talk about how we achieve the data scalability while maintaining data interactivity utilizing RayServe. So let me start by introducing our team. We all come from technical backgrounds, and we came together to tackle problems that we have frequently encountered before while working with the data, as well as solve problems that existing tools on the market doesn't address. So let me introduce our platform. So our Ikigai platform, we have built an easy-to-use AI-augmented data processing and analytics platform in the cloud. Within our platform, anyone can build powerful AI-enabled end-to-end workflow while staying within the comfort of the spreadsheets. While the tool has many features ranging from connectors to dashboards, everything kind of revolves around our data pipelines, as you can see in the middle. They consist of drag and droppable blocks where each performs a set of operations of data. You can pull, transform, and output data and those kind of operations. Not only do we have pre-built blocks with useful functionality such as select or join, all those like simple functionalities. We also have blocks where you can inject your own Python script to apply any custom business logic into the pipeline. With such sets of features, we enabled a few things: extraction of unstructured data and stitching together the unstructured data and then structured data, and then advanced analytics and with predictions and forecasting. And all this are backed by machine learning models. So here, even though we have a lot of stuff going on here, most of our problems comes from data prepping or data cleansing steps. So today we're going to specifically focus on the data pipeline aspect of our Ikigai platform. Here are things that we're going to talk about today. We're going to start by what is the Ikigai platform trying to achieve, why we choose Ray, how does RayServe resolve the challenges faced, how do we scale the RayServe inside of our Kubernetes cluster, how can Ray Client take us further. So the first topic, so what is the Ikigai platform trying to achieve? So we wanted to achieve mission critical data pipelining. So we faced many different users with all different business use cases. So how we deal with them is we let them inject a custom Python code into the dynamic data pipeline to enable flexibility. So one of the example here, as you can see here, one of the customers said, we want to collect all attached PDF files from emails every day and we receive today and use them as a source of data. And they want to run this pipeline every single day. Here, most of the steps can be done with traditional ETL steps, such as join or summary. But at some point, you need some custom Python code to do those of the specific business logic that you want to pursue. So by enabling users to inject their Python code, we achieve that flexibility. Next, we wanted to achieve highly interactive data pipelining. So in traditional ETL pipeline, it is really hard to see intermediate data sets. We let users to interact with intermediate data through a variety of mediums. For example, a user can code on the fly with the Jupyter Notebook at each step of the pipeline, or simply just view how they look like with the dashboards and charts. Last but not least, most interesting thing in my perspective is instantly browsable data pipelining. So this is very interesting challenge and problem we face. Not only our platform supports a fully scalable pipeline run, which handles a massive scale of data, but we also support a peaking of the pipeline, where we sample a few hundreds or thousands of data and then quickly deliver that to you at any point of the pipeline under a second. So unlike traditional ETL, we let users to interact with the data at each step of the pipeline under a second by enabling this. This includes, on the screen you can see the traditional tabular view of the data, or simply make a simple chart out of it. And also, by enabling users to quickly interact with data, they can also kind of debug the pipeline. So You can identify and fix erroneous step without waiting until the full pipeline is done. So which might take a few minutes to a few hours. So before we specifically talk about what kind of challenge we faced to achieve those three goals, we're gonna quickly cover why we chose Ray in the first place. So it was to earn massive scalability. So our company code base is primarily in Python and almost mostly in Python. And we wanted to earn massive scalability without having to completely overhaul our code base. And if you see the screen, there's a code base on the left. That's how our code base used to look like. It has all the business logic that we want to pursue for specific users, and those two examples there. All we need to do is do Ray init to vividly note that we are using the Ray cluster for this job. And then instead of invoking the regular Python functions, we invoke with the Ray's remote method. So as you can see, this was an extremely easy migration that we had to do, and it worked out greatly. So now we're going to dive into some specific challenges that we faced while we're trying to achieve those three goals above, and then we're going to discuss how Ray served helped us on the process. So before I dive into the challenges, I'm going to actually quickly talk about the Ray serve itself first. So Ray serve is easy to use and scalable model serve library built on Ray. It's one of the Ray's module. So we focused on the two characteristics of Ray serve. One is framework agnostic, and two is it is Python first. So Ray serve can serve not only deep learning models or any kind of a complicated machine learning models, but also it can serve arbitrary Python business logic. So since we're targeting our customers where they can have any kind of random business logic with the random Python functions, this kind of fits our build perfectly. So we decided to use one. I'll use this one. And second, Python first. As I said above, our company code base is entirely in Python, almost entirely in Python. So it being a Python first and pure Python code base, it was the right choice for us. So now we're going to talk about the challenges we faced. So first challenge, conflicting Python libraries. So since we let users inject their own code base to our pipeline, sometimes when different people in the same company collaborate in one pipeline, they can have different Python dependencies. So this became a little bit of a problem, not because of actual pipeline itself, because we can always create a different Python environment for each step, but it was for peaking. So we wanted to maintain that sub-second running time of the peaking, but if we were to launch a different Python environment every single time we run the pipeline for every single custom Python facets or custom Python steps, it becomes a problem because we cannot meet the sub-second running time anymore. So how we choose to cope with this was Ray serves optional argument where you can pass in the conda environment that you want to use. So here you can see in Ray actor options of the deployment decorator, you can specify the name of the conda environment that you want to use for this specific Ray serve instance. This means our pipeline will look like this. Each custom Python script step will be wrapped inside of a one Ray serve instance, which utilize a different conda environment specifically. So since they have their own space confined, they're not going to be a dependency conflict even inside of one pipeline. So the next challenge was the task overhead for peaking. As we briefly covered above, our platform supports two different types of data pipelining. One is scalable data pipeline run, where you want to run a massive scale of data. Two is a peaking run, where you sample data quickly for sub-second data interfacing. So the problem is our Ray cluster living in our Kubernetes cluster. When we want to submit a job to Ray cluster, it takes about 10 seconds for us to create not only the task definition as a Python file itself, but also the task submission itself to the RAID cluster takes about 7 to 8 seconds in total, in average. So the question is, if custom Python scripts are on RAID serve, how could we maintain a sub-second peaking time? So actually, this problem turns out to be the easier one to resolve. So RAID serve expose not only the regular RAID remote method of invoking your functions, but also expose the HTTP endpoint of your RAID serve instance. So if you see on the bottom, I'm calling RAID serve instance method with the HTTP request format. Here, I'm not going to suffer from task overhead because I'm using RAID. I'm not submitting a job to the RAID cluster with the standard channel. So how do we generate the HTTP endpoint for the RAID serve instance? It's pretty simple. So you instantiate the Fast API app, pass it into HTTP deployment decorator, and the decorator will append it to the existing serve instance you have. And then you specify it's going to be post method or get method, and you specify the subpath, which is deduplicate here. And then your RAID serve instance can support HTTP endpoint now. So with that challenges resolved, this is our Kubernetes cluster, how it looks like. So as you can see, we have a RAID cluster inside of our big Kubernetes cluster, and then we implemented this in-house solution for managing RAID serve instances, which is RAID serve manager. It's the microservice that does the following things: create, update RAID serve deployment, manages conda environment for all RAID worker pods or worker nodes, optimize the number of RAID serve instances based on dependency requirements. So since we're running all of this inside of the Kubernetes deployment, Kubernetes cluster, we faced yet another types of challenges, which is scaling the RAID serve and RAID cluster itself. So since that is very infrastructure related issue, our infrastructure engineer and cloud architect Amar will introduce you what kind of challenges we faced and how we resolved the RAID serve.
Hey guys, it's Amar here. Thanks so much, Jay, for introducing me. And today I'm going to discuss how we tackled that problem of scaling up RAID serve within our Kubernetes cluster and tackled some of the other steps along the way. So the first item on that agenda is auto-scaling, or spinning up worker nodes so that we have additional compute resources as user demand increases. One nice feature within RAID is that we found autoscale to be pretty easily accessible, and it's built in through the cluster launcher itself. So we didn't have to do a lot of work on our own to enable autoscaling of RAID worker nodes as needed. However, there is an issue that the autoscaling nodes present, and that is that these new RAID nodes come up without any of the other Conda environments and custom-built resources that our system requires. If you remember what Jay was mentioning when it came to custom Python logic within our pipelines, we do have these segmented Conda environments working all together within RAID serve to meet those needs. And when those new nodes come up, they don't have that built in. So in order to overcome that difficulty, we found one of the features within that same RAID serve deployment decorator to be extremely helpful in that case. And that is that we can define our Conda environments and all of their dependencies with plain text and within the definition itself, so that when the RAID serve manager realizes that a new worker node has been added, it can automatically just scale up a deployment instead of having to launch Conda separately and worry about which environments to handle. So the deployments themselves are built in with the Conda definitions. And now that we have an auto-scaling cluster that's able to scale up based on user demand, we ran into a few interesting complications. And the first of those came when we were analyzing our customer use cases. We realized that auto-scaling uniformly across all of our services was not the way to go because we found that it was a huge waste of resources when we have some services, if you look at this diagram, like the sort service that are highly popular, and then other services like the deduplicate service that receive a lot less traffic. It seems like an inefficient or almost like waste of resources to allocate the same amount of computational resources for both. So in order to tackle that, we were able to go again within the RayServe manager and actually modulate the number of replicas that we create for each service. And this gives us that granular level control, which can scale up a service as needed based on what we've seen from customer demand so that we don't waste resources on scaling up a service that's not going to get a lot of foot traffic. Another challenge that we faced when observing the user interaction was that we have these RayServe managers, like I mentioned, that are handling the RayServe worker nodes, and there is a possibility that multiple deployments that are sharing the same underlying resources can deploy updates at the same time to different versions. And as you know, this could create a possibility for non-deterministic behavior or a race condition. So in order to tackle that, again, what we were able to dig into the rich feature set of RayServe again, and they have an option within our custom service for enabling explicit deployment versioning. And this explicit deployment versioning lets us set exactly what the previous version should be at the time of launch and what the version we expect to be after the deployment is complete. And in that way, we've locked exactly what the beginning and end behavior should be. So even if multiple deployments get launched at the same time and they're all updating to different versions, whichever one doesn't get deployed first will realize that there's an inconsistency between the previous and current version, and then roll back and try or retry that deployment again in order to overcome the possibility for writing at the same time. So if we were to look at this diagram that we've presented here and kind of take a zoomed out approach, we'll see that within RayServe, we were able to leverage a lot of the existing functionality and features that they had to meet our own goals. And if we were to kind of go back to what those were, we're enabling a highly interactive data pipelining solution, as well as a highly scalable data pipelining solution that adapts to user demand and user requests. And within our Kubernetes system, we were able to work with the fundamental concepts of Kubernetes and integrate those with a lot of the functionality that RayServe provided us to let us make that happen. So that's the current state of our system right now. And I'll pass it back to Jay so he can discuss some of the options and cool features that we're looking to implement in the future.
Right. Thanks, Amar. So as Amar said, these are how we implemented and coped with the challenges we faced with RayServe so far. And then I'm going to introduce some immediate plan that we have potentially with RayServe and RayClient. So to briefly first introduce what RayClient is yet another module under the Ray project. So RayClient offers a remote client to connect to the Ray cluster. So it is more natural to dynamic task definitions. So in our cases, we need to generate the dynamic DAG pipelines per user's request. So in that case, it is really easy to construct like a dynamic Python object inside of the Python process. But if we wanted to create a Python file which represents a task, that itself can be a hard task. So by using RayClient, since all this logic will stay inside of the Python process, it becomes more natural to us. Two, it supports full Ray API. That means it will make our migration extremely easier because we don't really have to change a lot of things. So to demonstrate that, we have a small code snippet just to show how easy it will be for us. So let's say we have a RayServe instance definition here, and then you can, as you can see, all we need to do is add that one line to connect to the Ray cluster using RayClient, and the difference, as a result of this, what we're going to do is not create the Python file that looks like this and submit to the Ray cluster, but we're going to be able to just run this Python file locally, and then the Ray client would actually run the script as if we're already on the cluster. So as you can see, it's extremely minimal changes to utilize the full Ray API. So with this, one change we're going to have with our Kubernetes cluster, since we had an in-house solution, Ray Serve Manager, and that was the only microservice that we enable inside of our service cluster to talk to the Ray cluster. But with Ray client installed inside of all the microservices we have, we don't necessarily have to lay that limitation for all the microservices. We don't we don't have to go through Ray Serve Manager every time when we want to talk to the Ray's cluster or Ray Serve instances, which itself can be a bottleneck. So with this, all microservices and Python workers have access to Ray core and serve, makes us run more of a natural microservice environment. This concludes our talk. Thank you very much to Edward and Anyscale to help us tremendously along the process. And we're here for the Q&A for a while.